Our attention moves to renewal processes as we continue with the stochastic processes playlist. So renewal processes. So the first video on that will do a kind of introduction to the concepts of renewal processes. So what is a renewal process? That's the first question we need to answer as we move on here. A renewal process simply models events that occur repeatedly over time, where the time between events are independent and identically distributed as the time between events are IID. So a renewal process models events that occur repeatedly over time, and the time between events are independent and identically distributed. So by definition, we say that if we have x1, x2, up to x3 that are independent and identically distributed, non-negative random variables representing inter-arrival times, then we can define the arrival times as Sn, which is x1 plus x2 up to xn. That means that S naught is okay, of course, S1 is just x1, S2 will be x1 plus x2, S3 is x1. So it goes cumulatively like that. Then in that case, we then say that the renewal process is n of t, the number of arrivals, in a way, which is equal, or number of events, whatever it is you're considering, and that is the maximum collection of n such that Sn is less than or equal to t. The interpretation of this is that Sn is the time, it is the time of the nth event, right? So, of course, and first event x1, second event is x1 plus x2, third event is x1 plus x2 plus x3, and all of that. Then n of t is the number of events up to time t. Maybe it's number of arrivals, number of calls, or whatever else you might be considering. So the intuition is that we have, by way of intuition, examples of renewal processes will include things like machine replacements, light bulb failures, customer arrivals, system resets, and each event renews the system. So as you replace parts of a machine, that's a renewal. As you change light bulbs, that's a renewal. As new customers arrive, that's a renewal of the system, or having to reset a system and all of that. That's why we have it as renewal processes. So talking about key quantities for renewal processes, we have a renewal function which is given as m of t, and that is equal to the expectation of n of t. Then we have the mean arrival time, which is mu, and that is the expectation of x1. And then we have the long run rate, which is nt over t, and that approaches 1 over mu as t approaches infinity. Then we have a special case. We have special case we have a special case of renewal process in Poisson process. So if interarrival times are exponential, as we know for Poisson processes, that means xi is exponentially distributed with parameter lambda, and then we say that n of t is Poisson follows Poisson distribution with parameter lambda t, and in that case we say m of t is lambda t, being because we know m of t is expected value of nt, and we know the expected value of a Poisson distribution is lambda t. So this is the only renewal process with the memoryless property. So other renewal processes do not necessarily have the memoryless property. So talking about example one now, we have this. Suppose that mu is 2. That's the expected value of arrivals is 2. Then we want to find the expected number of renewals by time t equals 100. So the solution is easy. M of t is approximately t, the time, divided by the divided by the expected value. So M100 is 900 over 2, which is 50. So that means the expected number of renewals is approximately 50. Okay, so there'll be 50 renewals within time 100, whatever the time step may be, maybe it's seconds or minutes or hours or days or years or whatever. Then with that now we can actually, so if you take lambda to be 0.5 and take time to be 50, and then we can simulate this and get the renewal process which on a Poisson's for a Poisson case, and we have something like this. Of course, because it's random, as you keep running it, the shape keeps shifting, the process keeps changing like that. Okay, then we have a case of non-Poisson renewal process. So if we let xi be uniformly distributed with between 1 and 3. So the mean there will just be 1 mu, which is 1 plus 3 over 2, and that will be 4 over 2, which is 2. So this is still a renewal process, but it's not a Poisson process. And if we simulate that, you see that it is smoother than a normal, what a normal Poisson process will look like. So if you take t to be 50 and initial time is 0, and we keep running this, we keep, of course, the shape keeps shifting to, but it's not like the Poisson process we saw the other time. This looks a bit, it's a renewal process, but it's not Poisson. Then we have the renewal equation, which we are still going to consider in a separate video later on. So the renewal equation, the renewal function satisfies that m of t is f of t plus integral from 0 to t of m of t minus x dfx, where f of t is the distribution function of interarrival times. And then we have example 2 now. Talking about deterministic interarrival, suppose that the probability that x is equal to 1 is 1, like it's guaranteed that x is equal to 1. Then we say that the n of t is the floor t like this, and m of t is also the same thing. So in that case now we say that this is a perfectly predictable renewal process because it is, I mean, a probability of 1 is guaranteed. That's 100% chance that something is going to happen like that. That is why n of t is the number of events is equal to the expected value of it, which is the same. So this is a perfectly predictable renewal process. And then we have the elementary renewal theorem, which says that the limit as t tends to infinity of m of t over t is equal to 1 over mu. That means that for if you have m of t divided by t, the expected value of n of t divided by t, as t approaches infinity, it goes to 1 over mu. So the interpretation is that the long run average rate of events is 1 over the expected value. So this holds for all renewal processes. And then for comparison now, we have you have inter-arrival time, you have memorylessness and things like that. So for looking at the property, the kind of renewal process it is, and Poisson, whether it is the Poisson process and all of that. So for inter-arrival times, that happens for any uh independent any IID. I keep forgetting this IID thing. Independent and identically distributed. Yeah, independent and identically distributed. Okay, so for inter-arrival times. Then for Poisson process, it is exponential. So then for memorylessness, for renewal process, there's no memorylessness, but for Poisson, there's memorylessness. That's why we say it is the only renewal process that is memoryless. Then memorylessness, by the way, means that this current state is only the only thing required to determine the next state is this current state. So the states before the current state are not necessary to determine the next state. So talking about the distribution of n of t, that's the number of events now. For a renewal process, it is general. For Poisson process, it follows Poisson distribution. Then for complexity now, the renewal process is moderate, while Poisson process is simple, like that. And then we talk about applications of renewal process, where we have this in reliability engineering, queuing systems, inventory management, maintenance scheduling, and insurance modeling. So, and then we have a simple simulation for all of that here. So, simulation for long run rate. We already know that the long run rate ends up being like 1 over mu. It ends up being 1 over the expected value. So, then if you go ahead and do the simulation over a long time, so we already know that so for this kind of system that is uniformly distributed between 1 and 3, the expected value is already 1 plus 3 over 2, which is 2. And if you take the inverse of the 1 over 2 is half. So we already know the theoretical rate is 0.5. But then if we keep that aside and then we simulate the system, we go 10,000 processes like that, and if we run all of that, we see that you see that the estimated rate it keeps moving, keeps changing, but then it's hovering around the theoretical rate of 0.5 like that. So that means that as t tends to infinity, as time passes in the long run, the estimated rate tends to coincide with the theoretical rate. So the key takeaways from this the introduction to renewal processes are as follows. The renewal processes generalize Poisson processes. Then they are defined via independent and identically distributed into arrival times, and n of t counts number of events, be it arrivals, number of calls, and number of replacements, number of, and all of that, right? Then the long run rate, as we said, is 1 over mu, yes, 1 over the expected value. Then it is applicable in many reward systems, like reliability engineering, queuing systems, and all of that. So then we have practice problems here. Um, for basic understanding problems, if you let x1, x2 be independent and identically distributed with mean mu, you want to approximate m100. Of course, m100 is simply just going to be 1 over 5, which is 0.2. So just like that simulation thing we did just now. Then suppose interarrival terms have mean 0.5. What is the long run rate of the renewal process? That'll be 1 over 0.5, which is 2. Then define nt in terms of course, m100 is another way of saying in the long run, like at time 100, that's a lot of time steps away from the beginning, right? Define n of t in terms of Sn, then explain its meaning. We've seen all that. Then xi is exponentially distributed with parameter 2. What is expected value of n 10, like that? Then for a renewal process, what condition must the inter arrival times satisfy? We saw all that already. Then look at computation problems. Suppose mu is for the expected number of renewals by time t equals 200. That would just be 200 over 4. That's like 50. And of course, you can go on checking out the other questions like this. So if mu is 10, approximately, how long does it take to observe 50 renewals? That's 50 over 10, 5. So given mu is 2, estimate n500 using the elementary renewal theorem. That would simply be 1 over 2, which is 0.5, like we've been saying. Then we have conceptual questions like explain why the Poisson process is a special case of renewal process. Okay, we saw that already. It's the only case where you have memorylessness, yeah. Then what property distinguishes the Poisson process from general renewal process? Memorylessness, like I said. Is every renewal process a Poisson process? No. Justify your answer. Poisson process is memoryless while others are not. Then what happens to nt over t as goes to infinity? It approaches 1 over the expected value mu. Like give an example of a reward system modeled by renewal process, reliability engineering, queuing systems, and all of that. Then intermediate problem. Suppose xi is 3 with probability 1. Find nt and mt. Okay, so nt and mt will just be the same thing, right? Because you have a guaranteed situation there. Let xi be uniformly distributed from 0 to 2. Compute mu and estimate the long run rate. The mu is 0.2, 0 plus 2 divided by 2, which is 1. So the long run rate is 1, basically, because 1 over 1 will be the long run rate. Then if xi is exponentially distributed with 0. Find the expected number of renewals in time t equals 50. Then a system resets every random time with mean 8. Estimate how many resets occur in time 1000. That's 1 over 8 simply. Suppose mu is 1.25. Estimate the long run proportion of time between renewals. 1 over 2.5. And 1 over 1 divided by 1.25. So with this, we come to the end of this interesting video about introduction to renewal processes. Let me know how helpful this is for you. And if there's something else you want me to try out, feel free to let me know. If you have subscribed already, I thank you so much for doing that. If you haven't, why not go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. And if you want to become a member of the channel to get some special privileges like seeing some videos first or seeing some videos exclusively, or hanging out with me or getting PDF copies of my notes, you can become a member of the channel. Anyone that suits you best, feel free. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.